Hi everyone, my name is John Doucette. I'm a PhD candidate at the UBC MRI Research Center at the University of British Columbia in the Department of Physics and Astronomy. And today I'm here to talk to you about my package Ignite.jl, a brighter way to train your neural networks. So for this talk, what I'm going to do is start with the motivation for what problem we're solving. I'll give a high-level overview of the package and some of its features, and then we'll go through the documentation and look at some examples and walk through it. So first, some motivation. Neural network training. So training loops, I would argue, are often overlooked when you're discussing neural network implementations, and perhaps rightly so. There's sort of just a loop. You think, oh, that's trivial, it's no problem, I just implement that real quick and I'm off and going. So this is pretty much straight from the Flux documentation. It's a loop over a certain number of epochs. You have some data loader that you load some data XY from. There's a quick training step, so you take the loss, get the gradients, and then finally update your model. So, and this is a good point, throughout this talk I'm going to assume some familiarity with machine learning. Nothing too complicated, just the basic fact that you're going to do some gradient-based optimization. Here we're using the Flux package as an example, but in general this is the general style of training. You just loop over your data a bunch of times, possibly randomly, and you train. So what could possibly be wrong with this? Well, in principle, nothing really. I mean, all you need to do is sample some data, compute a loss, compute some gradients, update the model, and repeat. But then again, what if you want to track training losses? So this is, super easy to add. You have a vector of losses, you update it every time, you just keep track of them. It's no problem, super easy, you just modify your loop. Okay, but also, you're training your model and you want to evaluate it every now and then to get an idea of the progress. Because you don't just want the training loss, you want to try it on some evaluation data and so on. So every 10 epochs, let's say, you evaluate the model. So we add that in there too. Okay, well that's not really enough because you don't just want to evaluate it, like you'd want to save the model too. So let's say if your loss is below the minimum loss you've seen so far, we'll stop, we'll save a model to a BSOM file, and then we'll continue training. And so I think you can probably guess what I'm getting at here, but the majority of a training script really ends up being not training at all. So the training part is pretty simple. For a more complicated network, maybe you have a much more complicated loss and this sort of thing, but really this highlighted part here is the whole network training, and that's pretty much orthogonal to everything else you're doing here. Loading data, checkpointing, all these kind of things have nothing to do with the training step, and ideally you'd want to do something like factor this out and you get a nice sort of abstraction that way, and indeed you could do this. So this is a common solution, is you factor out the trainings, or not factor out per se, but you leave this as a loop since the loop is the easy part, and then you add in some points where you can call back, and maybe these things will wrap your checkpoints. So maybe before you start your epoch there's a callback, and before you start each iteration of your data batch there's a callback, and then after this one, there's just a bunch of callbacks, and these are super general, you can have them do anything. You set them up and then you pass them to you set them up earlier in the script or whatever. But this is also a little bit tricky because you have to decide when and how are they triggered. So here we've chosen kind of ad hoc where to put them. What arguments should they take? So do you just pass in the model, you pass in a data batch? Is there, there's different data for evaluation, testing, and so on. How do you compose these callbacks? What if you want them to fire, every 10 epochs, or, but at most every 30 seconds or something like this. This starts to get tricky a little bit quickly. And also tricky with callbacks is persistent state. So you might care about something like, the current epoch or the current iteration within the epoch, or furthermore, the current losses that have accumulated, or a certain number of, failed batches you've seen, all kinds of things. How do you deal with that in callbacks? And it's not obvious, and it's really hard to get right. And I think in fact Flux recently moved away from their train function altogether that was more callback based, and they just recommend writing loops because it's just too hard to get right generically, and it ends up being easier just to write these loops. But, is there a better way? So I would argue that there is, and that this callback way is not really a good solution, and this is more indicative of having a wrong abstraction. So what's an idea of a right abstraction? Well, what I'd like to propose to use here is a event and handler based system instead of a loop and callback based system. So this is inspired by a really fantastic Python library called PyTorch Ignite. So as the name implies, it's written for PyTorch, but it's really quite generic, and I've included some pseudo Python code from their documentation here, because I think this will be a nice way to overview what this actually does. So if you look so far, this really doesn't look so different. So you basically have a loop-like structure. While your epochs are less than the max epochs, you do some things, you loop over the data, and then there's a training step in the middle here. But the important thing are all these events. So what are these? So it's a simple and generic loop where the training step is actually just here, this process function. So this is something that you'll define elsewhere. We'll get to some examples later, but this is your whole training process, the gradient, update, the optimizer, all that is wrapped up in there. And then the cool part is the events are fired at nice set predetermined points during training, and you can hook up to these. So there's an event, iteration started. So this gets triggered, and then anything that has been attached to this will fire. So if you have some what are called handlers, these will get executed when this event is fired. So every batch of data is loaded. What happens is first you fire an event. If there's any handlers to execute, those all get fired off, so they execute one by one by one. And then once they're done, if there were no issues, we continue to the training step, run that as usual. That's just our stochastic gradient descent, some kind of optimizer like that. And then we fire another event that the iteration is complete. And this keeps going, going, going until we exit out of this loop, and there's another event, epoch completed. This keeps going, and at the start there's a corresponding epoch started. Similarly, when we enter this at the very beginning, there's just a plain, are we starting training and have we finished training? And that's it. So it's a really simple idea. It's actually a really simple package, but you can see in these next couple examples, it's actually very convenient, and it's really easy to get all kinds of complicated behavior with these really simple abstractions. And I've found it really nice for my work, and I hope people find this interesting too. So let's get to some examples, because this is much easier to understand than the sort of abstract description. So as you might have noticed from the last slide, so far it doesn't really look that different from callbacks. Like, how is your script actually any different in the end? Well, the difference is that you don't write that loop, that's abstracted away from you, and instead what you do is you create something called the engine. So the engine is something that wraps the process function, which really can be anything. Like I'm targeting this towards a machine learning audience because that's what I use it for and that's where it motivated from. But really this could be any sort of iterative process. But let's just stick with this example here. And so this process function is wrapped by the engine, and then there's also a training state. So this will keep track of what epoch you're on, what iteration you're on, like how long each iteration has taken, this sort of things, and the output from each call to the process function, for example. So this engine then, given these things, you can then consume a data loader, and that's done via Ignite.run function. So that's at the bottom here, and then you set the number of epochs, and by default, the number of iterations per epoch is taken just to be the length of the data loader. If it's an infinite data loader, you can set the number of iterations per epoch, and the data loader can be any iterable. So let's focus now on the engine creation part. So how does this work? So basically you write your training step as usual. So the arguments to the train step function are always the same. So it's an engine and a batch. The batch is just whatever your data loader iterator returns. Here we take it to be just a tuple of XY data. The engine is an instance of engines seen down here. This is defined by Ignite.jl, and then here we have a regular SGD type step. So We take a gradient and get a loss using Zygote. It's just a squared loss between some model of the data x minus y. So this is a very simple loss function. Do our update step, and then what we return is, in this case, a dictionary of a single scalar of the loss L with key loss, and this can be anything. So this is just stored in the engine, and this can be referenced from anywhere else in other callbacks, and we'll see later this can be quite powerful. So this is automatically stored in the output of the trainer state, and we can see how that's used in the further examples. So now that we have a rough idea of what an engine is, it just wraps a process function that does your training step. Let's see what else we can do. So the most important feature is that you can add events to this without changing the rest of the script. So first things first is this first line, is this trainer gets engine of train step. This is never going to change. This train step we've already defined, that's our training, that's done. We don't have to touch that. But now we can add all kinds of things afterwards. So let's say a really simple example here would be, we just want to print the latest training loss stored in the engine.state variable after each epoch. So I'm going to walk you through this code here. So what we do is, so we have this trainer defined, and what we do is attach events to this trainer, or event handlers rather. So to the trainer, this is the event, epoch completed. We're going to do a print statement where we print the training loss, where the training loss is here. So this is stored in engine.state, like this is a field of engine that every engine has, and the output is populated automatically, and we get the loss key, which again from the previous slide is output by the train step function. So this is nothing special, this is just what we returned, and now we're accessing it, and we can just print it. And then the most important part here is this epoch completed event. So this is defined by Ignite, and there's a whole list of different kind of events that we'll get to. And here, so what's going to happen is at the end of every epoch, it's just going to print this loss, easy peasy. And so the nice part here is nothing else had to change. Train step didn't change, the code below to run it didn't change. That's it. Now it's just every iteration it's going to print a loss, or at the end of every epoch rather. And we can do more stuff. So the same loss printing is here. We don't have to touch this, don't have to touch this, but now we can also say we can save the optimizer and the model every 10 epochs. So we make this event, it's the same epoch completed event, but now there's also some default keywords, every equals 10. So this is every 10th event, and the event is epoch completed. So this is going to be every 10 epochs. This code gets fired, save, model, and optimizer.bson. Easy. And this is also going to fire every single epoch. And so you can see how quickly you can sort of stack events and different different behaviors without having to modify any kind of loop. And this is easily like, every 10. There's also a keyword once if you only wanted to fire on the 50th epoch, say. There's all kinds of options like that. For a more advanced example, there's also custom event filters. So now, again, so pretend we still have all these other events there. There's no problem. We don't have to modify anything there. And now we just want to add this other event that if we ever see a bad loss after an iteration, we're just going to terminate the run. So we define this function, bad loss. So it takes an engine and event. So this is a custom filter function, just a regular Julia function. And so what we would do is we access the engine output. And if that is not finite, then we return true, and that means this is going to fire. So we make an event, iteration completed, with the keyword event filter, and we pass in this function. Then we add this event as normal, so we add this to the trainer. We add an event handler with this custom event, and when this event fires, if it does, we terminate the engine. So this is another function that just sort of gracefully exits training. Another really handy feature is that you can combine multiple events using Boolean logic. So you have this trainer and you want to attach this event that fires every 10 epochs, or if training has finished. So basically you have this event, you add this event handler, and this code will run either every 10th epoch or if it's finished. It's just really easy to combine these. You can also use the ampersand symbol for and. So for example, if you want something to fire every 10th epoch and say an epoch completed event where there's a custom filter that does something else. For example, maybe you want it to fire at most every 30 seconds. So you can say every 10th epoch and an event completed filter with a custom filter that returns true only after 30 seconds has passed. Like that's another filter that comes with the package. And you can see that in the documentation later. Another very common thing you want to do is evaluate on some test data. So here we're going to periodically run an evaluation engine with an evaluation data loader. So basically we define a new engine. So this is an engine where the process function is just passing off to this other function, eval model. So this will take the model in the batch, and let's assume your evaluation data for simplicity is just one single batch, and so we return this to the evaluator, and then the output of this, whatever eval model returns, will be stored in the evaluator output. And then so this engine we want to run on a different data set. So what we do is to the trainer we attach this event. So every 100 epochs we're going to run some evaluation. We're going to do some evaluation, and so every 100 events of the trainer run, we do another run of the evaluator. So say it's been 100 epochs, you run the evaluator on the eval data loader. So this is also nice because now you never have to worry about mixing up your evaluation data and your training data. This is a whole different loader. So you just run this on this, and then you can do stuff with the outputs from that. So in evaluator.output, or .state.output rather, will be the return value of this eval model. Alright, so that concludes the first part of the talk. So just to summarize, the Ignite.jl simplifies neural network training by replacing the training and validation loops with events and handlers. So the training step is factored out and the training loop is abstracted away. This pipeline is highly flexible and customizable. It's easy to add and remove events. You really just comment them out or delete them or add another one. Only the relevant code needs to be changed, so you never have to change your original loops or process functions in our parlance. And it's really simple and easy to maintain these scripts. That's from personal experience at least. I hope you'll feel the same if you choose to try it. And I mentioned this before, but the code base is very simple. It's a single 600-line file with lots of comments, so really probably more like 400 lines of code max. If you're interested and you like this package, feel free to contribute and or just post feature requests if there's things you'd like. It should probably be pretty easy to add. And I'm John Douce on GitHub. Here's the link here and a QR code if you want to scan that. All right, now on to some examples. All right, now let's go through some examples. So this is the readme.jl file that was used to generate the readme. So feel free to follow along if you want to go to the repository and start reading to follow along with the examples. So first things first, I'm going to load Ignite.jl and some other packages that we'll make use of. So the first example here that we'll use throughout is just a simple network that's a two dense layers followed by with a nonlinearity, a tanh nonlinearity in the middle. So we'll define that first, and we'll use the atom optimizer to train it. And so this model, which is just two dense layers, is going to try and learn this simple polynomial function from some training data. So let's define this f. And then we're going to have two sets of training and testing data. So we'll have some random data between -1 and 1, and then some uniform data for testing between -1 and 1 as well. And we'll define the labels. And then we'll define some data loaders that will, these are from MLUtils. So this will grab batches, shuffle it for you, and then same thing for the eval, but without shuffling on the evaluator. Okay, so now that we've got our problem set up, let's create our training engine. So here is a train step process function, which is very similar to the one from that you saw previously. So we just extract x and y from the batch. We take the mean squared loss, the squared loss between the data and the model prediction, and we minimize that using our optimizer. So here we have our model and our optimizer. They're being updated here, and we return this loss function. So let's define our trainer. And so just to inspect the trainer a little bit, we see that it has these fields. So the process function is this train step. State is an object type state from Ignite.jl. Then there's some no event handlers attached yet, and some other fields that we don't need to worry about yet. So we can see right now, trainer.state is essentially a dictionary with a bunch of useful fields. So right now these are not defined, iteration, epoch, etc. So let's run the trainer. And so this will print every time the epoch completes. These are really fast epochs, so it's finished very quickly, and then training's done. So training's done, but how do we know how it did? So that's where handlers come in, of course. So first we can take a look that something actually happens. So as you can see here, there's 25 epochs were ran, 25 to 100 iterations. The last value of the loss was 0.74, which doesn't mean a whole lot to you yet. But now, so that we have our bare bones sort of training set up, let's now start adding some events. So what we're going to do here is create an evaluator engine. So first we'll load online stats. This will be for keeping track of the evaluation metrics, since the evaluator is also evaluated in batches. This is pretty typical. Say if you're training like a convolutional neural network, you can't pass in your entire val set at once, right? You have to do batches somehow. So here is how we do that. In this case, we use online stats. This is just a choice. You can use whatever package you want, but it's quite convenient. So our evaluator is an engine that takes itself and a batch as the input. We make a prediction, and then what we're going to return is the true label y and the prediction y pred in a dictionary. And so remember that the evaluator is itself an engine. So to this we can also add events. So what we're going to do to keep track of these metrics is when you start the evaluator, so here's the started event, we're going to set a field, engine.state.metrics, and note that you can add fields dynamically to the state. So right now I have trainer.state. It has all these fields, and let's say I want to add a field, trainer.state.new field. So by default there's nothing there, but you can set it to 1, update it, etc. The state is completely up to you. So here what we do is we set this field metrics to be this mean value. This is from online stats, and this is uninitialized. So this is us restarting the state. And then every evaluation iteration that's complete, we're going to use this fit API from online stats, where essentially we just have the mean absolute error between the prediction and the true value. Okay, so that's just the evaluator running and accumulating some stats over the batches. And then, so, okay, I should actually run all this. So evaluator, add the handle. And then we're going to add a handler to the trainer so that this evaluator is run during training. So here we go. And then now, if we run the trainer again, we start to see some progress. Okay, so now what you can see is that every 5 epochs, the evaluator is run. So that's this run here, this evaluator is run. The loss on the test data is 0.08, goes down to 0.04, 0.02, 0.022, 0.021. We can see we're getting close to 0, and it's sort of stagnating a little bit, as we expected. And then now we can do all kinds of other things. So like before, we can Now we can go using bson, and every 10 epochs we can save the model. So here, epoch completed every 10, we're going to save the model in the optimizer state to disk, and we'll print that we did so. So now let's try running again. And so we did some more training, the loss value is even lower, and we see that this has been saved. So this model in optimizer state has been saved. What else can we do? So here we're just going to show some examples of what you can do in terms of adding multiple handlers to the same event. So this is just for documentation. Nothing's actually run here, but note that if you have an event like completed, you can add more than one handler to each event. So we can easily run like this dummy event and this one, and they'll be run in the order that you add them. So there's no issue with adding multiple things to the same event, which you might have gathered already, but just worth hammering home. Similarly, we have these Boolean flags. So if epoch is completed every 10 epochs, or your training is done, like I mentioned during the talk portion of this, you can quite easily add things like this. And here's another one that I mentioned during the talk. So this will be an event that's fired every 3 completed epochs, or after a completed epoch where the event filter is this throttle filter. So throttle filter is defined in Ignite, and what it does is it returns true at most every throttle seconds. So it creates an event filter that returns true if at least throttle seconds has passed since it was last fired. So this means that it'll do every 3 epochs, but in this case training is really fast. We want to do it at most every 30 seconds. In this case, training is too short for that to even be reasonable, but just we can show that we can add this, no problem. And finally, so this is more advanced usage, and I don't recommend doing this unless you have a good reason, but I mean, to be honest, it can be quite useful. So I've used this myself, so you can add in some custom events. So basically there's a type abstract loop event, and so the reason I say you don't only need this is because this is something that you add within your train step. Like if you really want to be able to get in there before and after the gradient step, say before and after the optimizer step, you want to just add a bunch of checks everywhere. In most cases, error handling will handle this kind of thing. You don't really need these events, but this is just an example, and you can put events basically anywhere. So all you have to do is define these events that subtype this abstract loop event defined in Ignite, and then you just add these to your code. So now every time train step is run, you write fire event on your like new defined event in here, write your other code as usual, you fire events wherever, and so now every time this is run, if you attach something to this, it'll run like normal. So this is just like, and they inherit these keyword arguments, so now you can add a code that every 10th backward pass you can do something. So maybe you want to track gradient norms, but it's too expensive to do every iteration, so every 10th gradient norm you add in here that you want to record it. And maybe before the optimizer step starts, you want to check that the gradients are not nan, or they're all finite, or things like this. You can add that in, and maybe once the step's completed, you want to check that the weights are still good. Normally these kinds of things are a bit too expensive to do every iteration, which is why I sort of cautioned in the beginning, but it's very useful, especially for debugging. So have at it, and you can add, again, these are arbitrary names. I just named them these ways because of where I put them in the train step here, but you can add any event you want that fires during training, and you can hook into it using the handler API. So that concludes my talk. Thank you for everyone listening. If you're interested, please feel free to download, play around. It's a very small package, so if you have suggestions or want to make pull requests, get after it, and I'd be happy to answer any questions if people have any. And yeah, thanks for listening to my talk. Happy coding.